So this one's a bonus, as you can probably see written in tiny blue letters at the top of the page. This one is a bonus. I was planning on doing this worksheet early on as an application to show if we did well enough with exponential equations. I was going to use this as a window into what we were going to be doing with the next unit, with Unit 3. We never actually got as good with exponential equations in class as I wanted us to. So this kind of got put into the back of my drawer as like a pie in the sky thing. Um, excuse me. What I am going to do with this is going to be the big introduction into Unit 3. And like I said, it's going to be a bonus video. It's going to be uploaded before Assessment 2.3. But again, this is just going to be a window. It's going to be an insight into what we're doing all the way through Unit 3. Geometry is doing a unit right now, which is basically a layup as far as their grade point average is concerned. I genuinely believe that if we can get exponential functions worked out, that this can be just as big of a layup for algebra. But we have to get exponential functions worked out. How do we know how to write them? How do we know how to recognize them? Because if we can do that, then like I said, this whole unit, this next 3 weeks leading into Christmas break is going to be a complete layup. So what do I mean by that? I'm going to work through these problems and show you what I mean. Keep in mind, this was in Unit 2. This was in the resources for Unit 2. So if you're having issues with graphs, if you're having issues with exponential functions, excuse me, I apologize. This was included in what you were going to be covering with Unit 2, but I just kind of held off. So starting off, in 2007, U.S. Census Bureau estimated the population of the U.S. to be 301 million, with the annual rate of growth about 0.89. Use the exponential function to find the expected population in 2025. All right. So this is what we're going to be doing all through Unit 3. We have to write an exponential function such that f of x equals a times b to the x. Now, ironically, usually finding b to the x is the hardest part. And so it's the last thing that we do before we declare victory and move on to the other problems. This one's probably going to be, we're going to start with b because it's the most direct one and it's the easiest thing to set up. So we have an annual rate of growth about 0.89%. What that means is that whatever our break-even point is, 1.00, we are getting 0.0089 more every year. So kind of going back to what I was talking about, whenever we're calculating growth rate, we're trying to go from the percentage of growth all the way back to the paragraph to the parentheses. The parentheses tell us how much we have gained or how much we have gained as a result of the growth, whereas decay tells us how much we have left after we have lost our rate of growth. So with this one, our annual rate of growth, so our b is going to equal whatever this is. So it's going to equal 1.00 89. I think that's what that, yeah. 0.89%. Yeah, okay. So now we have 1.0089. That's our rate of growth. Now we've got to figure out what our A is, and we have to figure out what our A is. We have to figure out what our X is. The good news is, just kind of like I've always explained, and I'm not sure if folks have picked up on it, but whenever you're dealing with time, that is always going to be your X value. And so, if you're dealing with time, that's going to be your X value. So we know that in 2007, that's a measurement of a year, and then 2025, that's also a measurement of a year. So the way that we want to do this is, if we're going to set up an exponential equation, we have to know a couple of different things. We have to know what the y-intercept is, and so we have to know what the A value is. Well, in 2007, we know that it's 301 million. So we have 2007, and I'm just going to write 301 because the question asked round to the nearest million. So I've got 2007, 301. But the thing is that 2007, 301, that's going to throw a lot of things off, because the designation of time is completely arbitrary. The number of years that's passed, that's an issue of time. That's going to pass no matter what. The 301, I mean, that's going to change. That's what we're tracking. That's what we're trying to figure out. But 2007 in years, like I said, that's going to throw our numbers off because in terms of math, we're basically saying that the number 2007 is tied in to 301, and it doesn't have to be. I'm not sure if you remember one of the earlier worksheets that I did where, because the numbers were so low and because they were so distorted, what I did was I changed the y-axis numbers to be like negative 0.1, and I started at -3, and then I worked my way up to like negative 1.5 or something like that. We can do the same thing here. And as a matter of fact, I think that's exactly what I'm going to do to the same thing here. I'm going to adjust the scales of time in order to make this equation a lot easier to work with. So anytime you're dealing with time, anytime you're dealing with any dimension of time, whether it's years, whether it's months, whether it's days, whether it's what have you, if you have something like 2007, set that equal to 0. If you're starting out in 2007, so in 2007, the U.S. Census estimated population in the U.S. to be 301 million. So what was it in 2006? No one, here we go, move it down there. So what was it in 2006? No one knows, no one cares. No data exists. Nothing happened before 2007. So if 2007, so 2007 is the very first year that we have data, that means that whatever the growth rate is, we start out at this number in 2007. So what that should key in on is if we're starting with 300 million in 2007, that gives us our initial value. But if we have our initial value and the number is 2007, how can we make that work? Like I said, that's easy. Instead of 2007, I'm going to say year 0. I'm going to treat 2007 as the very first year that I'm counting. 2007 is the year that I'm counting. So what does that mean? I go over to 2000, so that means I'm going up to 2025. You know what? One thing at a time. We're going to work on one thing at a time. So I've got my b, and I've got my a. So now I've got my function. F of x is equal to 301 times 1.0089 to the x. So now I've got my exponential formula. Anytime you're dealing with time, especially years, take the first year that you start with, set it to 0, and that'll give you everything you need for your initial formula. But now we've got a second part of the question. Now we've got a second part of the formula that we need to work out. Write and use an exponential function to find the expected population in 2025. So does that mean I set x equal to 2025? Oh, no, we're not doing that. The way that you want to think about it is if year 0, we have 301 million, and year 0 we're treating 2007 as year 0. All we need to do is find out the difference between 2007 and 2025. So I'm doing my calculator stuff off camera. So the difference is 18. Excuse me. So the difference between 2025 and 2007 is 18. That's the only figure that matters. We could be in year 3007, and this is year 3025. We're still only concerned about changes over 18 years. So going from 2007 to 2025, that's a time change of 18 years. If we're starting at year 0 with 301 million, then what that means is we're going to 2025 is year 18, and we need to know what this number here is. So the only way to do that is with our calculators. we're going to be doing some exponential modeling here. So let's go with 301. Oh, make sure I clear. 301 times 1.0089, up arrow 18. See what this looks like. 353. All right. So that will give us our final answer, 353 million. So again, how did we get here? What did we start with? We started with, we know that we had to have the final answer in the form of f of x equals a times b of x. Finding b ended up being the easiest thing to do because we were given the annual rate of growth is 0.89%. So if we know that the rate is 0.89%, that means that we can solve for the number that's inside the parentheses, b, as 1.0089. So we're in good shape there. Question then became, how do we find A? The way that we found A is basically by reading the question. So in 2007, the U.S. Census Bureau estimated the population to be 301 million. If you ever have a dimension that utilizes time, then that is going to be your X value. So if you're looking at time and you're putting it in the Y value, you're messing something up. That's the wrong thing to do. So any measurement of time is always going to be in your X value. So if X is going to be years, that means that Y is going to be what you're tracking. Yeah, so the population in millions is going to be the Y value. So if we know 2007 is X and 301 is Y, we originally set this up so it said 2007 and 301. But again, like I said, when it comes to time, you're interested in the change in time. You're interested in the passage of time. Whatever labels we have for the years are completely irrelevant. If we're interested in setting up an equation that can model the US population, we want to know the difference in population between 2007 and 2025. Like I said, it doesn't matter what labels these years are. What matters is that there is a difference of time of 18 years between them. So if the very first measurement we set is in 2007 of 301 million, that means that no time has passed. No years have passed, no cycles have passed, nothing has gone on. So at year 0, which is 2007, we had 301 million, which is where I got this 301. Once I understood I had 301, that meant I could put 301 in as my A value. I finally had a function that I could evaluate. What could I evaluate it with? Well, like I said, we're interested in the passage of time. We're interested in what happened over those 18 years. So if this is 0, then I have to set x equal to 18. Once I set x equal to 18, I had the function here. I just fed it into my calculator and got 353, which is 353 million. And that is the correct answer for that one. A lot of these are going to be, this is probably the first time you've seen a problem like this. You're going to see a lot of repeating problems and a lot of repeating problem types. So it may be a little bit daunting at first, but like I said, you're going to see a lot of repeating problems and problem types. Let's move on to the next one. An iPad Pro costing $1150. So when you buy it immediately, the price that you pay for it is going to be at time 0. So if you buy something, whatever the price is, that's going to be what the cost is at time 0. So that means that for f of x equals a times b of x, that means that we've already got our a, which is 1150, and then it can depreciate in value by 60% during the first year. So that means we have a decay rate of 60%. If we have a decay rate of 60%, that means that we're going to do 0.6 minus 1.00. That's going to give us 0.4. Converting that to a percent, going to give us 0.4. So that means we have 0.4 to the x. And so what that does is if it's 0, so go for a quick reality check. At time 0, this becomes at time 0, which would be when you bought it, when you initially paid for it, x equals 0, this whole expression becomes 1, and the value of it is 1150. All right, that makes sense. Time equals 0, value equals 1150. Good shape. But if x equals 1, that means that we only have 40% of the original value left after 1 year. If we only have 40% left, that means that we lost 60%, which makes sense because that is a 60% decay rate. So now we've got our initial value, we've got our decay rate. X is going to be number of years. Again, X is going to be time. X is probably always going to be time. And so what is it after 3 years? So we set X equal to 3. So f of X equals 1150 times 0.4 to the third power. We'll let this little fella take all the heavy lifting here. So 1150 times 0.4 to the third power, and it's worth about $73.6. So there we go. That's it. That's how you model it. That's how you get things going. That's how you read the problem and get the information from it. It's just, and like I said, it's going to be a lot of the same problem over and over and over again. The more problems you're exposed to, the more you'll be able to solve them. So let's keep it going. Let's keep the good times going. This person is currently Twitter's most followed person. In 2016, she had 89 million followers. So that should be a giant red flag to you immediately. Excuse me. That should be a giant red flag to you immediately because you're given a dimension of time, which is 2016, and she had 89 million followers. And so that means that at year 0 that we're counting, she had 89 million followers. So that means that for f of x, that's going to equal 89 times, and now we just have to figure out the growth rate. So the number is growing by 5.98% each year. So again, in 2016, which is a year, she had 89 million. So that's our initial value. 2016 equals year 0. She had 89 million followers. The number is growing 5.98% each year. So what that means is we've got, where to write this? So we got 1.00, that's our break even. But we're getting plus 0.0, yeah, that's right, 598 every year. So this is our break-even point where we gain nothing. We're getting 5.98% more than the break-even point, which means inside of our parentheses, we've got 1.0598. So yeah, 89 times 1.0598 raised to the x power. So that's our exponential equation in order to figure out, how many fans she has. And again, we started out, we're looking for red flags. We're looking for things that draw our attention. We're looking for keywords which will tell us what we need to know in order to plot the equation. She had, in 2016, again, whenever you see a dimension of time, that's a gigantic red flag. So 2016, which is a year, she had 89 million followers. So that means, obviously it means in 2016 she had 89 million followers, but that's our baseline. That's our beginning. That's where we're starting, is in 2016 she had 89 million followers each year. The purpose of the equation is to tell us how many she has each year. How is she changing every year? And so if that means that we're starting year 0 in 2016, then again, we are interested in the passage of time. We're interested in how x changes. And so in 2022 is 6 years away. And so what that means is we've gone through 2016, gained 5.9%, 2017 gained 5.98%, 2018, etc. So now we're looking through, and so the difference in time between 2022 and 2016 is 6 years. So 6 years, we're going to let x equal 6, and we're going to see how popular she is using this formula, which we derived from the information in the scenario. So 2022, yep, f of x equals 89 times 1.0598 to the, 6. 0.598, up arrow 6, 126 million. So that is the correct answer. So again, like I said, you're looking for the best thing to start with these problems is time. So if you're given a dimension of time and then another piece of information to track, that's probably, I mean, it screams initial value to me, but it depends on how the problem is written. Eventually, like I said, you're going to see a lot of the same problems over and over and over again. For example, the Census Bureau population one, we had the same thing as with the TikTok one. We had a dimension of time, we had a number, then we had a growth rate. So we started out year zero, we had 301 million with a growth rate. Then we wrote the exponential function using that information, and then we calculated the difference between 2007 and 2025, got 18. And so what that means is we're feeding in 18 years into this formula to see what the population could be. Same thing, same exact thing down here. Starting out here, you had a year that you started with, you had a number at year 0, and you had a growth rate. Then, once you wrote the exponential equation based on those 3 things, and that's all you need, you were asked about the passage of time. How does her fan base change over time? And that was what the question was. So that's that's a lot of what the growth questions are. So let's keep looking at some of the decay questions. Let's see. Set a 12-pound block of ice in the sun on a hot day. 4 hours later, came back and weighed the remaining ice. Its weight is 8 pounds. Ice melts at an exponential rate. Well, that really depends on the shape of the ice, but that's a completely different physics and heat transfer question. So 12-pound block of ice in the sun on a hot day. So what you're looking at is how does the weight change? What is the weight after how does the weight change? And then how does the weight change every hour? How does the weight change knowing every hour? You know what the initial weight was at time equals 0. It was 12. So what that means is f of x equals 12 times, and now we've got to find, now we've got to solve for b of x. Now we've got to solve for b. We don't have a growth rate that we can just plug in and do a quick mathematical operation for, but what we do have is we do have a point that is inside the text description. And so after 4 hours, so time equals 4, then 8, so at time equals 0, it was 12. So that's our initial value. At time equals 4, the weight was 8 pounds. So what does that mean? It means that we have 8 pounds equals 12 times whatever our rate is to the 4th power. So again, this is 4, 8. So if time equals 0 and weight is 12, then time equals 4 and weight equals 8 are points on that same line. And because of that, I can solve for b using this information. So I'm going to use this off the calculator. I'm going to use the calculator off the screen here. 8 divided by 12 is 0.67. And what I'm going to do this on the camera again, just to kind of show you all and get some more practice in. Second answer. There we go. So what I did was I hit second, and then if you hit the negative button down here, it feeds in the answer directly. So whatever your answer was from the previous question, it just plugs it in right then and there. As I mentioned in one of the earlier worksheets, I know I mentioned this in one of the earlier worksheets, the way that you get rid of, if you want to get b on its own, but it has an exponent, what you're going to do is you're going to take b to the 4th, and you're going to raise it to 1 over whatever the inside power is. So 1 over 4. What this does is using the exponential multiplication principle, 4 b raised to the 4, which is then raised to the 1/4 power, is the same as b to the 4 times 1 over 4, which is equal to b to the 1. So what that means is, if I'm going to do that and get b to the 1, that means that I have to take whatever 8 over 12 is, which is 0.67, and I also have to raise it to the 1/4 power, which is what I'm doing here. 1 divided by 4, and that gives me 0.9. Okay, so if I've got my b, I've got my a, that means I can do this. F of x equals, make sure I'm still on camera, equals 12 times 0.9 to the x. So that's our equation. But now make a prediction. What will the ice weigh after 6 hours? Well, that just means that we're going to feed in x equals 6. So f of x equals 12 times 0.9 raised to the 6th power. This is just a straight question of evaluation. So I'm just going to plug it in as I read it going from left to right. Times 0.9 up arrow 6. Okay, 6.38. And don't forget your labels, especially with word problems. So that is going to what the ice is going to weigh after 6 hours on the hot sidewalk. Again, it kind of depends what the shape of the ice is and how hot the sidewalk is and the ambient temperature on the outside. But maybe what do I know? I just have a background in heat transfer fluid flow from Navy engineering. And here we go. That's the that ended up being the final part of the worksheet. So yeah, this was supposed to be part of the curriculum for Unit 2, but this is what we're going to be doing in Unit 3. We're going to be looking at word problems like this, but we're basically just going to be coming up with exponential equations like this, putting in different values, and seeing what the results are. So again, it's going to be nothing but word problems. Hooray! I suppose. Nothing but word problems. And so the sooner we get solid and qualified with exponential equations, frankly, the better.